So let us start.
Okay, so since the title was not announced, by myself, I will speak about automorphism groups of complete algebraic varieties. The main question which I'm going to discuss is the following one. Suppose X is an algebraic variety. The question is whether its automorphism group is an algebraic group. Excuse me?
Is out is if oh, it's better.
Okay, so of course, if you ask this question for any algebraic variety, then the answer is clearly not. For instance, in the affine case, the answer is usually not. Well, it may be disputable what does usually mean, but write it like this. I guess that people here at this seminar know this kind of things quite well, but anyway, let me start with the simplest example, simplest possible example. Consider the defined plane and consider an automorphism of this defined plane, right? Given by this formula. So the point with coordinates xy is sent to a point with coordinates x, y plus f of x, where f is a polynomial over the base field of some degree. Let me say of degree at most n. So we have actually not a single automorphism, but an algebraic family of automorphisms parameterized by these polynomials, that is parameterized by points in the affine space of dimension n plus 1. Algebraic family of automorphisms of dimension n plus 1. And this means that the automorphism group of the affine plane contains continuous algebraic families of arbitrary p dimension. So it cannot be an algebraic group in any reasonable sense. And of course, this example extends to the affine space of any dimension, and also to other affine varieties, for instance, to flexible affine varieties, which are well known to people here in the seminar, I guess. So in the affine case, there is no chance to have a good answer in general to this question.
The general observation is if dimension of x is at least 2, and if there is a GA action relative group, then this works.
Yeah, so people here know this. Actually, yes, a similar idea can be applied to this kind of replicas. So,
but even if there are no GA actions, it looks like algebraic group, but it may be infinitely many connected components and so on.
Yeah, I will speak about connected components, but at least it may happen that for an affine variety, the group of automorphisms is the proper name is locally algebraic. This may happen, for instance, for tori, in other cases, but in general not. This is the situation in the affine world, but the situation becomes quite different if you pass to complete varieties. In this case, the automorphism group turns out to be an algebraic group, and even in a strict sense. So the algebraic group structure on the automorphism group of X, assumed X complete, is not a random one. It is a natural one in a strict sense, which I'm going to explain. So let me, it's a good time to fix some notation. Let me denote, I will work over some base field. I don't know whether this one here is visible from the corner. Okay. I will work over the base field K, which I assume to be algebraically closed and of characteristic 0. But this is just for simplicity for this talk. Most of the results I'm going to speak about are valid, maybe with some corrections, obvious corrections over any field. But let me stick to this standard situation for most of us that we love this world. Algebraically closed fields of characteristic 0. Even you may assume, if you like, that it's complex numbers. Then let me define what is an algebraic family of automorphisms. Yeah, so I'm still not assuming anything more. Algebraic family of automorphisms is a morphism from the product S cross X to X, where X is my variety, which I'm studying, and X is another algebraic variety, and maybe even more generally a scheme. An algebraic scheme. Well, when I'm speaking about schemes, I always assume, I always consider schemes over K, maybe separated, but I think that it's enough. Huh? It could be not reduced, of course. It may be even not of finite type. For instance, I may consider spectral local rings. So, in this sense, S can be a scheme. And the condition is that, so if you have such a morphism, then it induces a morphism of S cross X to S cross X in an obvious way. Just you map to the first factor here by the identity map on S. And the requirement is, maybe right explicitly, so on the level of points, S comma X is mapped to S comma phi of X, and this map should be an isomorphism.
Phi of S.
Phi of Sx, thank you. And this map should be an isomorphism of algebraic varieties or schemes. In particular, this means that for any given point S in big S, you may restrict this map phi on the section of this cross product with fixed point from here, and let me denote it by phi sub S. So it is a restriction of phi to S small s cross big X. And this should be an automorphism of X. So this is isomorphic to X, of course. And this should be an automorphism of X. So this precisely means that you have an algebraic family of automorphisms of X of this kind. But the condition for algebraicity is stronger than just saying that on each fiber you have an automorphism. You have them be compatible in a sense. So this match should be an automorphism of the product variety. Okay? Having this definition, we can associate to any variety or scheme S the parameter space for this family of automorphisms. You can associate to this S the set of all such families. With base space S, algebraic families of automorphisms, S cross X to X. And this gives you a functor from schemes to sets, but in fact to groups. Because the set of such maps is a group in a natural sense. You may take products, because actually this is just automorphisms. Let me say explicitly what is it. It is the group of automorphisms of this product variety, product scheme, S cross X, over S. So this means that these automorphisms should commute with projections to the base. By definition. And this is obviously a group. You can take compositions of automorphisms. So you have a functor from schemes to groups. And now the theorem, which maybe is the main theorem in my talk, theorem 1, due to Matsumura and Oort, 1967, says that if X is complete, then this functor is represented. Let me denote this functor like out, this fancy out sub X, which associates to each scheme S the set, the group of these algebraic families. So this functor out sub X is represented by a group scheme by the notation. Denote this group scheme out sub X. This is upright writing. So this is calligraphy. This is typeset. And this is a group scheme locally of finite type over K. This means that it is covered by affine neighborhoods, and each affine neighborhood is a spectrum of some finitely generated K algebra. This kind of group schemes
Is it countable?
I will comment on it. Yes. I mean, what do you mean by countable? The set of connected components is countable, but I will comment on it later. So this kind of group schemes are called locally algebraic groups.
There is slight comment on the definition that point-wise it doesn't define the map. That S times X maps to S times X via this formula. This doesn't define the mapping of schemes.
Yeah, I mean, I write this only on the level of points, but you have to, you need to have a map of schemes, a morphism of schemes, so you need to have a map on structure shifts.
Yeah. I mean, you can define it via that map to S times X to via the
You take a product of this morphism phi and the identity map from, or maybe a product of phi and the projection map onto X.
Yeah, but on the same pairs of points, so you found it.
Okay, I'm not sure that there are any more questions on this issue. Let me go on.
Is it difficult to explain what the spin functor is represented?
This I'm going to explain.
But before this elementary question, how do we consider this group? So we take automorphism of
Just
X.
group. Just group.
So the group
A
composition.
set with group law.
Yes,
This
but
is a
the
group.
composition is a composition of automorphism over any point.
Composition of morphisms. If you have one morphism, another morphism, you may take a composition. It acts as on points, as well as on points and on functions, on the structure. So just composition of morphisms.
But this will be a composition of automorphism of X over
No.
fixed point.
It's a no, it is a composition of automorphisms of this scheme. When you restrict to each fiber, you get an automorphism of the fiber.
And this is composition.
And this is composition of automorphisms.
You may say like this. So fiber-wise, it is a composition of automorphism of the fiber. But it is not enough to set an automorphism on each fiber. You need to glue them. So what does represented mean? Represented, well, it is a standard notion in category theory, but the people here, as well as me, are maybe not all familiar well with category theory. So let me explain. So this means the following. So we have this functor which associates to each S the set of, or the group of all algebraic families of this kind of with this kind of condition. So the representability means that this functor, so the set of algebraic families of automorphisms, each of these sets is in a natural bijection with the set of morphisms from S to this out X, to this represented scheme, and this correspondence should be functorial in S. So both things on the left and on the right hand side are functors from schemes to groups. So the set of these families is a functor, as I explained, and the set of these morphisms also. So it's a functor from schemes to groups, because you can multiply the morphisms by multiplication in the tangent space here. And why it is a functor? Because if you have another base S prime and a map from S prime to S, then you have a map in the reverse direction from families over base S to families over base X prime. You just compose these two maps. And here as well, if you have a map, the same map, or morphism, let us say morphism from S prime to X, then each morphism from S to out X gives you a morphism from S prime to out X. This is this bijection should commute with this kind of pull base. This is not just a bijection for each S, but a bijection functorial in S. This is what a representable functor means. You also may look, by the way, the set of morphisms from one scheme to another scheme is usually called the set of S points of this scheme. So I also write it like this, out sub X of S. So the set, or in this case even a group, of S points of this scheme out X. This is just by definition the set, in this case a group, of morphisms from S to this scheme. And this is, in my previous notation, this is fancy out sub X of S. So these two kinds of S points should be in a bijection, which is, in fact, this will be an isomorphism of groups. But this is not in the definition, it follows. This will follow from the definition. What does it mean in some down-to-earth terms? This means the following. Well, first of all, if you take for S just a point, if your scheme is just a point, a reduced point, then what is the set of S points of this scheme?
Point over K. Point over K.
Well, point over S or point over K is the same thing, just by the name. So points over K are, in the sense of this definition, are points of the spectrum of K. That is, points over a point. Morphisms from a point to a scheme. This is a point in this scheme, closed point in this scheme. And in this case, it is denoted like out x of k. Yeah. You do not write point here, you just write the field here. And the same notation is used for any affine scheme. The spectrum of some ring, some algebra. Then instead of writing the scheme here, you write the algebra, whose spectrum the scheme S is in this case. This is standard notation again. And once you have this bijection, you get the same as the set of algebraic families of automorphisms from with the base S, where S is a point. But an automorphism family whose base is just one point is a single automorphism. So if you have this functorial isomorphism, then this is the same as this, and this is by definition just the group of automorphisms of X. Okay? So it is in this sense in which the group of automorphisms of X is an algebraic group. It is just the group of k points of this scheme.
And what we will write if S is equal to K?
If S,
Is equal to K.
well, K is not a scheme, K is a field. If you speak about the spectrum of K, this is the point. This I have explained right now. And this is by definition the same as this.
So if it is a fine line, then we write A1.
You may write A1, or you may write here K of some variable in brackets.
No,
For
this
defined
is not correct.
schemes,
You should apply your out to a scheme, and you cannot apply it to a field, as you explained.
no, I mean, in any case, when you write like this, let me write it explicitly. If S is a spectrum of some algebra A over K, yeah, then you write so X of X. Actually, this works for any scheme, but let me stick to this scheme of automorphisms. Out X of A is by definition the same as out X of S.
This is
where
just
X is
notation.
It's just notation. Just notation. Okay, I hope I explained what is representable in formal terms, but let me explain it in down-to-earth terms. In particular, you may take for S this scheme itself. And by the way, maybe did I write this notation somewhere? Okay, so if you take for S this scheme itself and take as a family or as a morphism from S to out X, just the identity morphism. Let me put denoted like, yeah, just identity morphism. So Fano notation. Then to this morphism in here, there corresponds some algebraic family of automorphisms of X parameterized by this scheme. Let me call it the universal family. Let me denote it by phi some universal family from the cross product out X times X to X. The universal family of automorphisms parameterized by this scheme. And the universality property is the following one. if you are given any family of automorphisms with any base S, so any point in here, thanks to this bijective correspondence, this gives you some point in here. So this gives you a unique morphism from S to this out sub X by this correspondence, by this bijective correspondence. And actually this diagram commutes because of functoriality of this correspondence. If you so we have to substitute a different notation in this formula. So if you replace S by this, and if you replace S prime by this, then then the family F universal corresponds to the identity map, then this family, by functoriality, should correspond to the composition of the identity map with this map phi. And this is phi itself. So the functoriality gives you that this diagram is commutative. And this is actually just another definition of the representing object. So you say that this functor is represented by some scheme if there is such a universal family satisfying this universal property. Any other family is obtained from the universal one by pullback, by a unique pullback. This is exactly the representing property. What I want to add here, yeah, this universal property, as well as the initial definition of representing object, implies that this representing object, this scheme out S, is unique up to an isomorphism. If it exists, it is unique up to an isomorphism. Well, this is actually an immediate corollary of universality. If you have another universal, another representing object, then you have another universal family. So you have two universal families, and they are obtained from each other by unique pullback. So you have a unique pullback here, unique morphism here, and unique morphism to the opposite side. And the composition of these two morphisms should be identity, because it is how the universal family is obtained from itself. Of course, it is obtained from itself by the identity pullback.
I'm very sorry, but we more or less know what is a group of automorphisms.
Yes.
We want to prove that this is locally algebraic.
Yes.
Do we need all these funny things for this?
Actually, yes. How to say? I mean, maybe you can adjust the arguments to cook something handmade, but still, I mean, essential things will be hidden in this functorial behavior, because it is this property which actually allows you to produce such a scheme, such a group. By the way, first results on this algebraicity of the automorphism group, I think they were proven in a different language, but I mean, the group was quite technical, so I mean, it was not easy to understand what ideas were behind. And the proof using this representability of functors, of automorphism functors, is ideologically very clear, actually, as I hope to explain. So I'm going to present a proof of this theorem in the particular case when X is a projective variety. By the way, I should have said this at the very beginning of my talk. So it is an expository talk. It is based on these two papers by Michel Dillon on structure theorems for algebraic groups. It is published, I don't remember where. find it, but it is also an archive, so it is easier to find it in archive. And the second paper is, again, another expository paper, notes on automorphism groups of projective varieties. It is, I even don't know if it is published anywhere, even is, I don't know if it is on archive, because the homepage of Lesieutre at the University of Grenoble, this is the address of this homepage, where you can find the file of this paper. It does not contain a link to archive.
But these are some lecture notes.
These are not even lecture notes. These are some paper written after lecture, after some lecture course. It is not exactly the lecture notes. It is some expanded version. But yes, I think that it is nowhere published even on archive, which is a pity, because everyone knows archive, but not everyone knows the homepage of John. While the notes are quite useful. So let me present the proof. In the projective case. So I assume that my X is not just complete but projective. And the proof in this case is actually goes back to Grothendieck. More precisely to his construction of Hilbert schemes. There was an exposition in the seminar in 1961 where this construction appeared for the first time. So proof using Hilbert schemes. And let me recall, of course, not much details. What is a Hilbert scheme? So consider yet another functor from schemes to sets. So to any scheme S, we can associate the set of all flat families Z in the product S cross X. So flat means that the morphism, the projection map from Z to S, is flat. So you have a subvariety or even subscheme, closed subscheme in this product S cross X, and you may view this subscheme as a family of subschemes in X parameterized by this parameter space S. And the theorem of Grothendieck says that this functor from schemes to sets is isomorphic. Well, it is again representable. It is represented by a scheme which is called the Hilbert scheme of S. It is this functor is isomorphic to the functor of morphisms of points, morphisms from S to some scheme and some X. Well, this is called the Hilbert scheme. Again, this Hilbert scheme as a representing object satisfies some obvious universal property. There is a universal flat family of subschemes in Z, parameterized by this Hilbert scheme, and any other flat family is obtained from the universal one by a unique pullback. So what is important is that this Hilbert scheme is a disjoint union of projective schemes.
Varieties.
Schemes. Well, I said that X is just a scheme, so you cannot restrict yourself just to varieties. The Hilbert scheme exists, and it is a union, disjoint union of projective schemes Hilb sub x comma p, where p is a Hilbert polynomial. This open and closed subscheme, distinguished by the Hilbert polynomial, parameterizes those flat families for which each fiber has the Hilbert polynomial p. So, parameterizes flat families such that each fiber as a subscheme in X has Hilbert polynomial.
This is some statement. So in flat family, Hilbert polynomial is constant.
Exactly. If you have a flat family over a connected base, then the Hilbert polynomial of fibers is constant along this flat family. It is a statement from algebraic geometry. So if you have connected S, then it is mapped to one of these components. It cannot be mapped to the union of several components. And these guys are indeed projective schemes.
And the collection of these polynomials is countable.
The collection of these polynomials is countable because Hilbert polynomials take integer values at integer points, and the family of the shape of such a polynomial is well known. It is a sum of some binomial coefficients with integer linear combination of some binomial coefficients, and of course the set of possible Hilbert polynomials is countable. So this is not a projective scheme itself. Not a projective scheme of finite type, yeah? Even not a projective scheme, because projective scheme is of finite type by definition. So, but it is a countable union of projective schemes. I will not explain the construction of the Hilbert scheme. It would be a subject of yet another talk, a single talk. But well, roughly speaking, the idea is very simple. You want to parameterize subschemes in X, and X is a projective scheme. Even you may replace X with a projective space. If you restrict to X, then you just get a closed subscheme here. So if your X is just a projective space, you parameterize closed subschemes in your projective space with fixed Hilbert polynomial. A subscheme is defined by the ideal, the homogeneous ideal, in the homogeneous coordinate ring of a projective space. It's just a ring of polynomials. And actually, if you fix a Hilbert polynomial, this means that you fix dimensions of homogeneous components of this ideal, at least starting from some big degree. Actually, you may choose one and the same degree for all subschemes with a given Hilbert polynomial. It is again a result from algebraic geometry, so you can choose this degree uniformly. So the homogeneous component of the defining ideal in this degree actually defines, well, maybe if you take this degree sufficiently big so that the ideal is generated, the ideal sheaf of this subscheme is generated by global sections from this component, you may say that this component itself defines your scheme uniquely. And this component is a subspace in the space of homogeneous polynomials of given degree, of fixed dimension. So a point in the Grassmannian. So basically, each subscheme that given a Hilbert polynomial is distinguished by a point in some Grassmannian. And after that, you want to impose the condition that this subspace indeed is a component of some ideal that given Hilbert polynomial. And this condition is expressed in some multiplication. So this subspace should generate an ideal. Some with given Hilbert polynomial, and this means that some multiplication maps, when you multiply this subspace by other homogeneous polynomials, then so the rank of these maps should be restricted by some number. So basically, you have to impose the condition that some minors of some matrices are vanishing. And this gives you the Hilbert scheme as a subscheme in the Grassmann. This is a very rough idea of how Hilbert schemes are constructed, how the existence of Hilbert schemes is proved. Of course, there are many technical details on this way, but this is so. This is not something very mysterious, actually.
But to say what is this, say for projective plane, this is not easy.
It is not easy. It is easy to explain why it exists, but it is not easy to explain how it is defined by equations in some projective space. Of course not. But it is even not necessary. The main point of this representability property, Hilbert schemes as well, is that to study Hilbert schemes or other representing schemes representing some functors, it is necessary and sufficient to use this representability property. You can study everything on the level of functor of points. The points, the tangent spaces, whatever. So this is indeed a very strong property which can be used to study this kind of things. Now let me explain the proof. At least the sketch of the proof. So suppose we are given an algebraic family of automorphisms, say pick phi, a map from S plus x to S, satisfying this condition that if you extend this map from the map to the map from S cross X to itself, then it will be an automorphism over S. Yeah? So this you may consider the graph of this morphism, the graph of this map. Better to say the graph of this morphism. Let me denote it by gamma sub phi. It is a subvariety, subscheme in S cross X cross X. And on the level of points, it consists of the points of the triples S, X, Y, such that Y is equal to phi of Sx. So the graph of this map phi. Since it is a graph of some map from S cross X to X, the projection of this closed subscheme in here, the projection of this graph to the product of the first two factors, to S cross X, just forgetting about what? Is an isomorphism. So the inverse map from here to here is given by this formula. And since it is an isomorphism, the projection to S from here to here is flat. So this projection is obviously flat, and this is isomorphic to this. So you have so the graph of your family of automorphisms is actually a flat family over the base S, and you may consider the respective point, the respective S point in the Hilbert scheme. So you see that the set of algebraic families over the base S, in my notation, this is out S, out X of S, this fancy out. This is not a scheme, just a function. Embeds into the set of, like this, into the set of S points of the Hilbert scheme of S cross X. So this graph is a flat family over S and in here. So it gives you an S point of the Hilbert scheme. This map sends your family phi to its graph. And now, conversely, if you have some family flat over S, in this product x cross s, x cross x, you want to understand when this family is a graph of some map of this kind, of some family of homomorphisms. So you need actually two things. You need this projection be an isomorphism, and the projection onto the product of the first and third factors, so forgetting about x, forgetting about the argument, should be an isomorphism. So we have two projections. Here you have a point s comma x comma I, right? And this point is sent here to s comma y. And here to s comma x. So these two, so you may write that z is in here if and only if, and these two projections are isomorphisms. Actually, this basically says that as well as x, sy is the image of x under some morphism. X is also the image of y under some morphism, because the second projection is also an isomorphism. So this means that on each fiber, and even on the level of schemes, if you define, as we did before, if you define this map from s cross x to itself by this map, just adding the factor s here, then this map phi should be an isomorphism over s. Okay, and so the final step in proving the representability is to observe that this condition, that both projections should be isomorphisms, is an open condition. This is intuitively, well, I cannot say obvious, but you can believe that it's an open condition. But formally speaking, the proof is based on the following lemma. In the notation as before, it says that if the fiber of this family S, of this family Z, over some point small s, is mapped under this, or this doesn't matter. These projections are more or less have the same structure. You just forget about the second or the third factor here. So if you restrict this map on the fiber, so you fix your S, then you get a map from the fiber Z sub S to S, right? If you fix S here, you get a map to S. So this map on the fiber is an isomorphism. If this map is an isomorphism for some point, small s, then this map becomes an isomorphism over some neighborhood of this point. There exists a neighborhood S naught containing S, such that the map from S naught, the map from Z restricted to S naught cross X is an isomorphism. In particular, this means that this map is an isomorphism for any fiber close to this one. But not only this. This statement is more strong that all these isomorphisms glue up to an isomorphism over S naught of the whole family with this trio of them. Okay? So this statement, this lemma is actually a version of Nakayama lemma together with some properties of flat morphisms. So essentially it is a statement in commutative algebra, and I don't want to prove it because it is more or less technical. But what does it give it to you? If you apply this, lemma to the
About this lemma. So,
yeah.
From dimension count, you understand that the map is finite.
But I mean, you need to have a schematic isomorphism. Finiteness is not enough, of course.
Yeah, but you can get rid of finiteness via Hilbert for the numbers. Through the information from Hilbert for the numbers.
No, the proof here doesn't use Hilbert polynomials. It just uses flatness, the properties of flat modules.
Yeah, but
Actually,
but flatness for finite morphism means that the number of fibers, the number of pre-images is constant.
it is only a property of flatness, but it's not equivalent. It depends on the base. Here, the base may be arbitrary. So just finiteness or dimensions of fibers are not enough to guarantee flatness. Because you consider flatness over any base. You just use the definition of flatness, the properties of flat modules. Again, I say it is technical. For instance, this lemma, the proof of this lemma can be found in Pollard's book on rational curves, where he explains what is Hilbert schemes, gives proof, a scheme of proof of the existence of Hilbert schemes. So, what does it mean for us if you apply this lemma to the universal family? The universal family with the base, whose base is the Hilbert scheme itself, with base which is the Hilbert scheme itself. So this is a subscheme in product x cross x times x times x, like here. So if you apply this to the universal family, then essentially this lemma says that the set of points in the Hilbert scheme which correspond to automorphisms, so the family satisfying this condition, is an open subscheme. So in the space of parameters in this universal space, this lemma gives you an open subscheme. And therefore, we get that the scheme representing the functor out x is an open subscheme in the Hilbert scheme.
And what does it mean? It means that we should take this Hilbert scheme for x cross x, right?
Mm-hmm.
And for automorphism group, some component has the same dimension as component of these Hilbert schemes, and some Hilbert schemes component are not represented, have empty.
Yes, of course. And even this guy is not well, it is a connected component, but it is not an irreducible component. Hilbert schemes may be reducible, and this out x subscheme is an open subscheme. Well, if you take the some connected component of this automorphism group, it comes from an connected open subscheme in some of these schemes. But this may be reducible, so this open subscheme is not dense. So even some irreducible components for given P can be not represented by some. Can contain no points from the automorphism scheme.
But another question. Take a projective variety with trivial automorphism.
Yeah.
What does it mean? It means that the Hilbert scheme of S cross X has a component consisting of flat modules, of course. So no flat families.
No, not trivial families. Yes. Okay. So I hope I explained the idea how this representing object can be found as an open subscheme in some Hilbert scheme. So you just associate to each algebraic family of automorphisms its graph, and this gives you a point in the Hilbert scheme.
Yeah, about next question about components. If you fix super for the one now, then of course we can have components that do this. Yeah. So can
If you fix Hilbert polynomial, then some irreducible components of the Hilbert scheme may intersect. This is exactly what I said. And this guy is maybe
but can it happen that one coset is some open set in one component and the other coset?
I don't know any example of this, but why not? So far I see no obstructions. Maybe, I don't know even if people studied this question. So far I see no reason why not. Okay, we proved that this functor of automorphisms of X over some base is represented by some group scheme. And actually, since this group scheme is an open subscheme in some Hilbert scheme, it is locally of finite type. So since it is a group scheme, its irreducible components are the same as connected components, because all points are smooth. In characteristic 0 at least, either in characteristic 0, or all schemes, group schemes of finite type are reduced by a theorem of Cartier. So there exist smooth points, and by transitivity of the action of the group on itself, all points are smooth. This is standard argument in the theory of algebraic groups. It applies as well. And this means in particular that connected components in here are the same as irreducible components. And each irreducible component sits somewhere here for some p. Yeah? And therefore it is an algebraic group. It is a group scheme reduced of finite type. An algebraic group in the usual sense. And all other components are the cosets of this algebraic group. So this in particular proves that this group scheme is a locally algebraic group. So its identity component is a usual algebraic group. Maybe I should write it as roller.
And maybe one more question about that. Maybe you can reformulate the idea of the group in some elementary terms. Something like any automorphism preserves Hilbert polynomial of something. And the set of transformations which preserve Hilbert polynomial of something is finite dimensional scheme. This is something like this?
Well, more or less I did it here. So any automorphism gives you, for any automorphism, you may consider its graph. It is a sub scheme, even if your X is just a variety, graph is a sub-variety in here. And this sub-variety gives you a point in this Hilbert scheme, or over K, just a usual geometric point. In this, if you believe in existence of this Hilbert scheme, then this sub-variety gives you a point in here. And now, this statement that a sub-variety in here corresponds to some automorphism means that the projection of this sub-variety to both vectors, here and here, are isomorphisms. Okay? If you have just one projection is an isomorphism, then this means that this sub-variety is a graph of some map. But if you want that this map to be an isomorphism, you need that the second projection should be an isomorphism. And the statement of this lemma just says that this is an open condition. So the points in this Hilbert scheme for which both projections are isomorphisms are an open subscheme. And this gives you the structure of, at least the structure of an algebraic variety on the set of automorphisms. This is in down-to-earth terms. But, I mean, still for this you need the existence of this guy. And also, actually, to study properties of this automorphism group as an algebraic group, you need this scheme representability. So you need that this functor, this group indeed represents the functor of families of automorphisms with base being any scheme. I will show you. I think I will show you why this is useful to consider not just varieties but also schemes as base in a couple of minutes. But before that, first of all, just a standard remark, two standard remarks. I did not explain what is the group structure. I just explained why this set of algebraic families of automorphisms is represented by a set of morphisms from the base to some scheme. But I didn't explain why this scheme is a group, it's an algebraic group. Why there are morphisms giving you multiplication and inversion and so on. But this is actually quite standard, again, in category theory. If you have a functor from some category to groups, and you have an object representing this functor in the same way as before, so the set of, so to any object in your category, to any object S, you associate some group depending on S factorial. And this group is identified with the set as a set. It is identified with a set of morphisms from your S to this guy. Then this guy is automatically what is called a group object. It is equipped with morphisms giving a group structure in the sense of this category. I don't want to explain it now, though it's quite easy, but I don't want to spend time on it because it is very standard. You can find in any textbook if you Google for group objects in a category. So very easy argument actually. So let's believe in that this guy is not just a scheme or locally algebraic variety, it is a group, locally algebraic group. Morphisms giving you multiplication and inversion. And now another standard remark is that since we are working over an algebraically closed field of characteristic 0, we may identify by Hilbert we may identify the variety scheme out X with its set of k points. It is completely defined by its set of k points. And this is quite standard. And a naive viewpoint on algebraic variety is just a set of points, which is in a more clever way a set of points, k points in some scheme. But let me write it down that we may identify some x of k with, well, first of all, let me write it like this. We may identify out x, this scheme out x, with its set of k points. And the latter set is the same as a set of k points of this group functor, which is by definition the set of algebraic families of automorphisms from the product point cross x to x, which is just the same as the set of automorphisms of x. So in this very sense, this guy is an algebraic group. It is a group of k points of some algebraic group scheme under this identification.
No, this is not an algebraic group. The connected component is an algebraic.
No, even not an algebraic, a local algebraic, a group scheme. Yeah, local algebraic. Now corollary of this theorem. Yeah, by the way, I give a sketch of the proof in the projective case, but in general, for any complete X, the proof due to these people, Matsumura and Oort, is based on completely different ideas. But still, I mean, you will not like it because it is based on some axiomatic characterization of representable group functors. So, if you want your group functor, this one, be representable, then you just check some list of axioms. And they prove that this list of axioms is necessary and sufficient. And they check this list of axioms for this automorphism functor.
In this way.
Yes, in this way. So,
but you said that something was proved in 50s.
not in 50s. The first paper I know, and by the way, I know all these things from this Brion's paper. So I always refer to one of these two papers when I quote cite some other results. The first result on this to maybe I forgot, but you can find in one of Brion's paper who proves that the identity component of an automorphism group of complete variety is equipped with the structure of algebraic groups. And he proves it, again, considering algebraic families. He first proves that the dimensions of these algebraic families are bounded from above, and then somehow he hooks up a structure of an algebraic group on the union of these algebraic families of automorphisms. So something like this.
This is 65.
But, I forgot the date, 64, maybe 65, but this is, I mean, quite technical, and it is not easy to tell what is the main idea of the proof. Some very technical considerations.
And in 50s, maybe it was complex analytic case.
Yeah, complex analytic statements were known before, in the algebraic statement. Okay, so what is the corollary of this theorem? One of the corollaries is that, as we already mentioned, the identity component of this group scheme is just an algebraic group, connected algebraic group in the usual sense. And the component group which is by definition the quotient of x modulo the identity component, is discrete, of course, since it is the component group, and counting. Finite or countable. Countable means infinite, at least in some convention. So that would say finite or countable. At least for Brion, countable means infinite because he writes the statement exactly like this. I follow him. So the only thing to be proved is the last one. Why the component group is countable. It is done like this. First of all, observe that your variety x, since it is a complete variety in the usual sense of finite type, it is defined over some countable subfield of K.
And all these arguments with countably many Poincare polynomials is not enough.
It is not enough because you don't know what happens, or maybe... yes, of course, yeah. I mean, in the projective case, of course it is enough. Because in the projective case, we know that this guy sits in this Hilbert scheme. And the Hilbert scheme is a disjoint union of countably many projective schemes. And this is an open subset in here. So yes, in the projective case, it is enough to refer to Hilbert schemes. But since I formulated the theorem for any complete X, let me explain how this corollary is proved in this generator. But it is equally easy. Because first you observe that your X is defined over some countable subfield of your base field K. This is clear because it is of finite type. So all coefficients in defining equations, defining the open charts, the open affine charts of your X in some affine spaces, all these coefficients, there are countably many of them. And if you span a field by all these scalars, then you get a countable subfield of your base field K. You may make it algebraically closed. If you close it up, you obtain an algebraically closed countable subfield. And now we can work over this smaller subfield. And then, since over an algebraically closed field, every scheme of finite type has a point, you see that your group, your scheme, group scheme out X, is the disjoint union of cosets for the identity component. And the representatives of these cosets, these GIs, can be taken to be defined over this smaller field K model. say? Yeah, I mean, still, it is not clear why this is clear already. Well, okay, let me explain like this. Why this set is already countable? Because why this set is already countable. You may say like this. To each, so each of these GIs is actually maybe just G. Each of these G's is an automorphism of X defined over K naught. So if you associate to this G its graph, gamma sub G, it is a subvariety in X of K naught cross S X of K naught. It is defined, it is a subvariety defined over K naught, and you may consider it as a subvariety, as a subset, again by Hilbert Neutralization, we consider it as a subset in this product set of K naught points of X to itself. So, and the set of all such subvarieties actually is countable. Because for instance, you may cover this guy with finitely many open affine charts. And if you intersect this subvariety with any of this chart, this is a closed subvariety or subscheme, whatever, in this chart, and it has a defining ideal in the algebra of polynomials over the field K naught on this chart. This guy is countable. And the set of ideals, any ideal is finitely generated, so the set of ideals is also countable. This is why this the set of these G's is countable. This is how to explain that this set is countable, and so you have countably many representatives. This means that this group is countable. Okay. So, by the way, when I'm supposed to stop?
15 minutes. Okay?
15 minutes. 15 minutes. 37, yeah? 37. 1937. Okay. So now I think I will be more sketchy. And first of all, I promise to explain why this schematic viewpoint is useful.
Yeah, can you give example
I can give you an application of this schematic viewpoint. So the proposition that if this guy is an algebraic group, or at least a locally algebraic group, we may consider its Lie algebra. So what is the Lie algebra of the automorphism group or of X? I think you guess the answer. What is the answer? Can anyone tell me except Volodya? Exactly. So the Lie algebra of the automorphism group is the Lie algebra of all vector fields on your variety X. Vector fields are global sections of the tangent sheaf. Or if you like, derivations. In algebraically, this is the same as derivations of the structure sheaf. So on each open subset of X, you have the algebra of regular functions, and you have a derivation of this algebra. And these derivations should coincide on the intersection of open affine subsets. So this means that you have a derivation of the structure sheaf. To give a vector field is the same as to give a derivation of the structure sheaf.
But I was surprised that for affine varieties this is not true. For affine space, the Lie algebra of the automorphism group is not the derivations of the polynomial problem.
This is because the automorphism group is not representable, I guess. And also it depends on how you define the Lie algebra of the automorphism group. Because it may be a matter of definition. Now, how to prove this statement? Actually, it is almost tautological, or at least very easy. Proof is like this. So you may consider the algebra, what is called the algebra of double numbers, K of epsilon, with the relation that epsilon squared is 0. It is a two-dimensional local algebra, Archimedean local algebra over K, Let me take for S the spectrum of this local algebra. It may be viewed as the first order infinitesimal neighborhood of a point on a line. So if you forget about nilpotence, you get just a field K. So this scheme has a single point, a single closed point. But also, since you consider this nilpotent epsilon, actually you may look at this scheme as a point and a tangent vector at this point. A single tangent vector given by the choice of this epsilon. If you reparameterize, if you multiply this epsilon by some scalar, then of course this vector gets multiplied by the scalar. So informally, you may think about this scheme as a point and a tangent vector in an abstract sense. Now, what is the tangent space of any variety y at some point y? It is exactly a point of this y with values in this scheme S. So the S point or the K of epsilon point. But not any one. If you fix this point y, then you have to impose some condition. Namely, if you specialize the parameter, sending it to 0, you have a map from K of epsilon to K. And this gives you a map from y of K of epsilon to y of K. Just to the set of closed points of y. This means exactly that when you consider a point in here, you have a map from S to y, a morphism from S to y. But if you restrict this morphism to the closed point, you get just a map from a point to y, just a point in y. And this point should be this very y. So the tangent space of y at small y is exactly the set of all points with values in this scheme of double numbers, this algebra K of epsilon, sitting over y under this map. Okay? And why this so? Of course, for people who are not quite familiar with this language, of course, it can be expressed algebraically. So those people who study algebraic varieties in have some naive understanding of algebraic varieties, also have an understanding what is a tangent vector. At least if your variety is affine, then the tangent vector at some point is exactly the derivation of the coordinate algebra of your y at this point. So you have a map from O of y to the field, satisfying the Leibniz problem. Now, what is a point in here? Algebraically, again, if y is affine, if y is not affine, then you may replace y with some affine chart. But algebraically, a point in here is a homomorphism from the coordinate ring or from the algebra of regular functions on y to this algebra. Just an algebra homomorphism. And this homomorphism sends any yes, exactly. This homomorphism sends any function on y to what? You want to also to use this condition. So when you restrict when you restrict to the closed point, you want to get the point y itself. This means algebraically that when you specialize epsilon to be 0, that is when you map k of epsilon to k, putting epsilon equal to 0, then this map should correspond to point y. This means that this map should be evaluation of functions at this point y. So the initial map should be of the following form: f of y plus epsilon times something depending on f, linearly. Some linear function which I denote like this, d of f. And now, to say that this very map extends to the algebra homomorphism, so you may embed it in of y tensor k of epsilon, and extend it to this by k of epsilon linearity. And if you want this map to be a homomorphism, then it says exactly that this function delta is a derivation at y of your coordinate algebra with values in k. And this is by definition the tangent space of big Y and small y. So I have explained to those who didn't hear it before why this tangent space can be viewed as a point in this set of schematic points of Y. Now let us come to our state. So we want to understand, so for brevity let me denote this automorphism group by G. So we want to understand what is the Lie algebra of G. The Lie algebra of G. By definition, it is the tangent space at the unity. Yeah? And we view this tangent space and the unity in this way. So it is a subset in the set of k of epsilon valued point of G, such that when you specialize epsilon to 0, you get G of k, this should map to identity. So those k of epsilon points which sit over the identity point of G. These are exactly the tangent vectors. And now, to explain what is this, we use the representability problem. What are tangent vectors? Tangent vectors at the unit. So, by definition, they are points, k of epsilon points of G, and the k of epsilon points of G are exactly the families of automorphisms of X over the base S. Yeah? So these are the maps from S cross X to X, and you may extend, as I explained, you may extend this to the map from X cross X to itself to S cross X, which is an automorphism over S. So this kind of diagram should be commutative. These are tangent vectors at any point. And to specify that these tangent vectors are points at the unity, you have to use this condition. So when you specialize epsilon to be 0, this means that you consider the map, the morphism, from a point to the scheme S. And this gives you, of course, the family, so the fiber of this family at this point will be just an automorphism of X. And this automorphism should correspond to the unity element. It should be identity. This is on the geometric level. And on the algebraic level, you have to consider the structure shift. So you have the structure shift in here of X, of epsilon square is equal to 0. You have again the structure shift in here. This isomorphism corresponds to isomorphism from here to here. And since this is an isomorphism of over S, this isomorphism of structure shift should be linear over k of x. So on k of over k of epsilon. On k of epsilon, it should be constant. It should be identical. K of epsilon linear. And this condition says that when you restrict to constants, yeah. So what is this? Is O of x plus epsilon of x. If you restrict to this first summand, or maybe not restrict to project. If you project to this first summand, because the map on functions should be in the reverse step, from up to down. Then this should be identity. Now, what kind? So if this guy that we denoted, say, by alpha, then this would be alpha star. What is this alpha star? If you consider how this alpha star acts on functions from O of x, forget about this for a while, you get, since modulo this ideal acts on something, it is identity, so you should get f plus epsilon times something, and this something, which I again denote by delta df, should be a derivation. So to claim that this map is a homomorphism is equivalent to claiming that the map D is a derivation. Derivation of the structure shift. Okay? And this is how one proves that the Lie algebra of the automorphism group scheme is the same as the algebra of vector fields. Okay, I think I have just 1 minute left. And what can I say in this last minute?
You promised us to prove that this discrete group can be not finitely generated.
I didn't promise to prove it. I said very accurately that I would discuss some of these issues. If you want me to discuss this issue, I have to borrow yet 5 minutes more, because it is not possible even to explain the construction in 1 minute.
Okay.
And I will just give you a construction without any proof.
5 minutes it will be subtracted from your next talk, so okay.
Okay. This basically means that I have to give more and more talks. It's shorter and shorter. Example. Yeah, actually I have a lot of other examples, but this I see I have no time to discuss. Maybe it's not as interesting as this example. So, example of a smooth projective variety X such that the component group, well, even I can say that the whole automorphism group is discrete. That is, the identity component is trivial. And we know that it is countable, finitely countable, but in this case it is countable and even not finitely generated. So the first construction is due to Lesieutre. The archive paper is 2016 and it was published next year. Such a variety of dimension 6. And after that, 1 year later, Dean and Pugizo constructed an example of dimension, in fact, of any dimension starting from 2. But first they constructed the 2-dimensional example. And from it, they could easily the examples in any dimension. So we consider this 2-dimensional example. So a smooth projective surface having discrete and not finitely generated automorphism group. So the construction is as follows. By the way, it works over complex numbers. And at least the construction itself cannot be extended to any algebraically closed field of characteristic 0. There should be sufficiently many transcendental elements. So at least to reduce to complex numbers, there should be sufficiently many transcendental elements. So it is not clear, at least for me, whether this example can be constructed for any base field algebraic closed of characteristic 0. Let it be complex numbers. So you start from taking 2 elliptic curves, A and B. 2 elliptic curves which are not isogenous to each other. So they cannot be obtained from one and the same curve by some finite homomorphism. So basically, you may take most randomly 2 random elliptic curves of complex numbers. And you have an involution on this product variety. This is a 2-dimensional Abelian variety. You have an involution, just inversion. The involution sending AB to minus A minus B. This is an automorphism of 2nd order of this variety. You take the quotient modulo the cyclic group of order generated by this automorphism. You get a singular surface, and this singular surface has 16 singular points. So these points can be seen as follows. So when you restrict this involution, taking inversion to one of the factors, so you get a 2nd order involution on an elliptic curve, and this is a ramified double cover over the projective line. So you have this cover over A. This is the projective line, and this is my elliptic curve. There are 4 ramification points. So these points say A sub I. And the same for B. Here you again have 4 ramification points for the double cover of B over the projective line given by this inversion method, by modding out this automorphism. So the points, the ramification points, I will denote them by B sub J. And when you take the quotient for the product, then of course pairs AY BJ, they are fixed by this evolution, and they go to singular points. And the images of the fibers, say some AI cross B under this method, will be projective lines, rational curves. So you have 16 rational curves. Not 16 by 16. You have 8 rational curves. These curves will be denoted so far no notation. So you have 8 rational curves intersecting in 16 points. These 16 points are exactly the singular points of this singular surface. And now you blow up them. So blow up the points AI, B, J, modulo this involution. So the images of these pairs in this quotient surface. And you get a smooth surface, X naught, which is known as Kummer K3 surface. This is a K3 surface. And it contains rational curves, which are strict transforms of these rational curves. There are 8 of them. So it contains strict transforms of these rational curves. AJ is the strict transform of these curves, and BI. The strict transform of this curve, and also 16 exceptional curves, which are which sit over these blown up points, CIG. So the picture will be now like this. So these are AJs, these are BIs, and also you have these exceptional curves coming from this you see all intersections here in this picture. So this is Cij. Okay? Now what you do next? You choose a point on intersection of sum of ai's, or sum of aj's, say this one, and sum of cij's, say this one. You take this point, so let it be P, and you blow up this point. You get yet another smooth surface, x1, which is isomorphic to x naught outside P, and instead of P, you have an exceptional curve, say E. The points in the exceptional curve correspond to tangent directions of your initial surface at this point P. So you have the point which I again exhibit on this picture as this point, corresponding to the tangent direction of AJ. And you also have another point on this exceptional curve, corresponding to the tangent direction of Cij, this one. So the strict transform of Cij will intersect the exceptional curve E in this point. This is Cij prime. Okay? And now you take yet another point on this exceptional curve, say Q, distinct from these two, and blow it up. So
The story should not be short.
blow up, it is the end of this. Blow up a point Q on E outside the union of strict transforms of this and this. Outside AJ prime, union Cij prime. Okay, you blow up this point, you get yet another exceptional curve, and this will be your X.
From this picture, it's immediately clear that the group is not.
If you give me yet another 5 minutes, I can explain you at least a scheme how to prove that it is no fine. But I think that you will not. Huh?
The idea, right?
The idea, okay. I mean, the idea, yes. Still, I need some couple of minutes to explain you the idea. The idea, well, maybe not the idea, but rather a scheme. Let me
Finish my sentence.
let me finish my sentence, and please do not ask questions before I finish. Okay, so roughly the idea is as follows. This is a very standard thing, a K3 surface, and this group of automorphisms is well known, it is finitely generated. The point is that this finitely generated automorphism group may contain infinitely generated subgroups. And the trick is to realize such a subgroup as the automorphism group of something blown up. This is the idea. And more precisely, you do the following. So you have, you may prove, first of all, that the automorphism group of X can be embedded in the automorphism group of X naught. So any automorphism of X can be pulled down to the automorphism of X naught. And more precisely, if it is pulled down, then of course it should fix the point P. If the automorphism of X comes from an automorphism of X naught, it should fix the point which is blown up. Another statement is that now it is the statement about automorphisms of this Kummer surface. The automorphism of X naught fixing P automatically preserve this curve, AJ. Now you have the isotropic representation. The stabilizer of P in the group of automorphisms is represented in the tangent space. So you have a map from this group to GL of the tangent space. This is the isotropic representation, which I denote like this. Another claim is that it is diagonalizing. It is isomorphic to the direct sum. So since this curve is preserved, then the isotropic representation on this curve is a sub-representation here. And the complementary representation is actually the isotropic representation on the tangent space of this second curve.
And these spaces are one-dimensional.
Of course, this is two-dimensional, these two are one-dimensional. So this representation is diagonalizing. Now, you may consider the kernel of the isotropic representation. And it is clear that it consists of automorphisms in here, which act trivially on the tangent space. And since they act trivially, they lift to the blow-up. First, they lift to the first blow-up because they fix the point P. And they also fix the tangent directions. This means that they fix each point in this exceptional curve. And then they lift to the second blow-up. So this group is a subgroup in here. This group is a subgroup in here. And one can prove that this is a finite group extension. And finally, you may consider the kernel of the isotropic representation on the curve. Of course, contains this one. And it is contained actually in here. Yeah? So they prove, is a proof that this group is not finitely generated. While this extension is again finite. And now, if this is not finitely generated, then this subgroup of finite index is again not finitely generated. If this is not finitely generated, then this group is again a finite extension. It is also not finitely generated. This is the scheme how they prove.
But this is based on some deep knowledge of the automorphism group of case-theory surface.
Yes, of course. I mean, this means, well, maybe not. You need not to know the whole automorphism group. You need to study. You need to actually, how to say, how they prove that this guy is not finitely generated. They construct a surjective map. Maybe I can write it here. They construct a surjective homomorphism from this group R, A, J, comma, P to the group of automorphisms of this curve AJ, because it is preserved. Yeah? The group of automorphisms of AJ fixing the point P, which is, what is it? The automorphisms of projective line fixing a point. Automorphism of affine line. In fact, they even, it can be proved that, so you get a map to this semi-direct product, GM cross GA. And actually, they prove that in here they have, yes, in here they have just one, because this is the kernel of this isotropic representation at the point E. So this multiple should be one. So you get exactly the map without this factor. You get exactly the map to the affine line. And what they prove that the image of this map contains some infinitely generated subgroup of Q. Explicitly given. Something with denominators increasing denominators. I mean, if it were finitely generated, the image would be finitely generated, and then it could not contain, since it is a commutative group, it could not contain an infinitely generated commutative subgroup. So this is how we do this.
So nothing like automorphism of case-theory surfaces is an automorphism of some lattices, not like...
No, this is not used. But of course, geometry of case-theory surfaces is used. some statements about K3 surfaces and more general algebraic surfaces. They are used, so it is just a scheme. It is not a complete proof, but I think that the idea more or less is clear. How to follow these steps and check something at each step to obtain the result. The initial example of Lesieutre dealt with rational, so he started with a rational surface, and then did some machinery to produce the 6 dimensions. And here they start with a non-rational surface. Product of the curves.
Thank you very much. We have a lot of time for questions, so please.
A lot of time. Till the next Wednesday. Некоторые тут остаются до следующего доклада.
So, if no questions.
So I would like to ask. So when we consider the connected component of the identity of the variety, we tell that it's algebraic.
Yes, in the usual sense.
Yes. What about, so is it known when this group is linear?
Good question. I can take here another half an hour to continue my talk, because it is what I plan to tell you.
But seriously, maybe we can plan the
Yeah, I can, well, if you,
Not
actually,
now, not now. Maybe we can plan the talk.
actually I could, because I don't know if it will occupy the whole seminar, but so the experience says that maybe yes, it will more.
Minus 5 minutes, you remember?
Yes. Even this maybe not enough.
So let us plan the talk after.
So if you like, I can tell more about this, yes.
No, this is a very interesting topic. That we can plan this next year.
Okay, but I can explain you the picture in private.
Okay.
What about, for example, non-reduced?
Well, this should be positive characteristic.
Yeah, of course. Maybe that's yourself by calculating.
Well, I don't remember. I don't want to cheat. I don't remember. I'm pretty sure that you will see such examples in one of Brion's papers, because there are many examples actually. He discusses this